Slideshow.
Okay, here.
Yeah.
Okay, interesting.
I'll give you a signal at 22 minutes. Oh, sorry. Just not a minute. 20-minute call. I'll give you a signal at 15 minutes.
All right. Good morning, everyone. Can you hear me well? Yes? Okay, excellent. All right, so I will be talking today about negative responses in Ferroics, and I actually have 3 stories to tell you. The first one will be about negative longitudinal piezoelectricity in hybrid organic and organic hydrazinium cobalt formate. Then in the same material, I will tell about the negative linear compressibility, and the final story will be about negative capacitance regime in antiferroelectric lead zirconate. All right, so here is a hydrazinium cobalt formate. We have been working on this material for quite a while. It's hybrid organic and organic perovskite. So this material is dynamically disordered at high temperature. It's in PNMA space group, and then at temperature 343 Kelvin, it undergoes phase transition into polar PNA21 space group. So here the direction of the polarization is along the C-axis, and we were interested to study piezoelectricity in this material, and for that we used density functional theory computations. We applied uniaxial stress either along C direction or along B direction or along A direction. So here's our computational result. I'm going to begin with the stress that we applied along the C direction right here. And the blue symbols right now give you the polarization response to the uniaxial stress. What you can tell me right away that, look, this slope is actually negative. And the negative slope, of course, means negative longitudinal piezoelectricity. So here it's very clear if I apply tensile stress, that will actually cause the polarization decrease, and this is quite counterintuitive response. So the subject of negative piezoelectric response has received quite a bit of attention in the literature at this point. Experimentally, there are just very few materials that have been demonstrated to have negative piezoelectricity. So among them PVDF and its copolymers, two-dimensional layered ferroelectrics, as well as some samples of hafnia. Computationally, however, there have been quite a few predictions, including predictions in ABC ferroelectrics, van der Waals layered bismuth-Taylor halides, and as well as some hafnia predictions. So what has been known so far? For example, the origin of negative longitudinal piezoelectricity in ABC materials was traced to the interplane between different contributions. So here the piezoelectric coefficient was decoupled into 2 contributions, one from clumped ion response and another one from internal strain contribution. And in this work, a lot of materials have been investigated, and it was found that the first contribution, the clumped ion contribution, is actually negative for all the materials investigated, whereas the second contribution could be either positive or negative, and it's actually the interplay between the two that decide on the sign of piezoelectric response. So we followed these ideas, and we computed both contributions for our hybrid material. So here I will focus on this result, and if I focus on longitudinal piezoelectricity, I can see that both clumped ion and relaxed ion contributions are negative. But can that tell us the whole story? Probably not, because in our study we're actually looking at a very wide range of stresses. So we have to look at some other mechanisms, especially the ones that would be responsible for this negative relaxed ion contributions. So we were thinking about the possibility of volume playing a role in that, because these materials are quite soft and we can expect a change in volume. So perhaps that would be responsible for the slope. So to investigate that, we actually computed the response of the dipole moment to the applied stress. And as you can see from this blue data, you can see that the response of the dipole moment is very much correlated with the response of the polarization. So we don't believe that this is the volume that is responsible for the effect. The next point for us was to take a look and actually decompose the response into two contributions. One will be coming from the framework and another one will be coming from the molecule. So let's take a look at this set of data once again. And the empty or open symbols here will give the response of the framework to the piezoelectric coefficient. And we can see that indeed it's actually the response of the framework that decides the sign of the piezoelectric response. On the other hand, the molecule plays very minuscule role in this case. So I will also now bring your attention to the other set of data that I have here. Let's take a look at this panel. This panel reports response of the polarization to the uniaxial stress, but now the stress is applied along the transverse B direction. And what we can see here, it's actually quite counterintuitive because the tensile stress along the B direction will cause the polarization enhancement, which is quite, exotic phenomena, but at least it would be in agreement with the negative response that we observe for the longitudinal coefficient. On the other hand, if now we apply stress along the A direction, another one of the transverse direction, so here we will observe the response of the negatives of the opposite sign. With what it means here, it means that if we apply tensile stress, we will actually reduce the polarization in the perpendicular direction, and this is something that one would expect. So what we realized that this material is actually quite unusual because it can exhibit everything. It can exhibit negative longitudinal piezoelectricity, and it can exhibit both positive and negative transverse piezoelectricity. So, and in this case, we can once again take a look at the decomposition into the response of the framework and response of the molecule. And actually for the transverse direction, it's quite opposite. The framework almost doesn't play any role. It's entirely due to the contribution of the molecule that we observe the different sign of the piezoelectric slope. So we further took a look at the structural origin of that effect, and it turns out that if we compress material along the C direction, there will be a huge change in the polyhedral angle right here, the one that I give with the red symbols. And it turns out that what happens if I compress along the C direction, there will be oxygen octahedral tilts, and those tilts will deform your framework, and that is what will make contribution to the sign of the piezoelectric coefficient in case of the longitudinal response. On the other hand, for the transverse response, we actually found that it's the tilt of the molecules that is responsible for the sign and for the response of the material to the applied stress. So we realized that this material actually exhibits very anisotropic response to the applied stress, to the applied deformation. And it turns out that this is not the only exotic phenomena that originates from that anisotropy of mechanical response. We also carried out a study when we applied hydrostatic pressure to the same material. And here I report the dependence of the lattice parameters on the pressure that we applied. And it turns out that the C lattice parameter as well as the A lattice parameter shows the usual response. They decrease in response to the pressure. But if we take a look at the B lattice parameter, it actually shows the opposite trend. The B lattice parameter increases in response to the hydrostatic pressure, which is known as negative linear compressibility. So this material, in fact, exhibits negative linear compressibility. This is the zoomed in plot, and we can see that first it starts with the usual positive compressibility, and then it changes the sign. So it turns out that this phenomena can be well described if we think about this material as the one that has wine rack type of geometry. Right here, you can see that wine rack type of geometry. And that type of geometry is typically described using a strut hinge model. So here you can see the struts, which are relatively stiff, and then you see this hinge angle. And if we compute the evolution of strut length under pressure, we can see that the strut length decreases as it should be, so material responds to the pressure. But on the other hand, if we follow the evolution of this hinge angle, we can see that in response to pressure, the hinge angle actually increases. And what happens in this case is illustrated in the schematics. So if we can increase the hinge angle, you can see we can increase the B lattice parameter. And this is exactly what happens here. So this hinge angle turns out to be rather flexible, which again, we can trace to the tilt of the oxygen octahedra here. And the final story that I have here to tell is about negative capacitance regime in antiferroelectric lead zirconate. So what I have here, I have schematic view of the free energy of a typical antiferroelectric. So we have several minima here. The global one is, of course, our antipolar phase, and the local minima correspond to the polar phase. We can turn this dependence into the equation of state. And from the equation of state, we can find two regions of negative slope, which is the same as negative susceptibility or negative capacitance regime. So these areas are shaded, and we can see that this shading is actually associated with a maximum in the free energy. And this is the area that system tries to avoid. The system doesn't want to live in that thermodynamically forbidden region. So we were thinking that what if in computations we can do anything? What if in computations we can actually promote the system into this thermodynamically forbidden region? So we can apply extra large field. We can do that in computations. We can apply fields at extra high rate and see what happens. We tried all that, and the result was very boring because every time in lead zirconate we will see loops like that. By the way, this is effective Hamiltonian finite temperature simulations. So every time we will get the response like that, which is red, which doesn't have any negative slopes. And then we recall that what happens in ferroelectrics, it's oftentimes the role of depolarizing field that brings us into that negative response region. So we decided to just bring in the depolarizing field in this case and see what's going to happen. So here we just use the bulk lead zirconate, but we introduce depolarizing field, and that brings the internal field. Well, the internal field here in the sample is going to be the sum of two contributions, the applied field and the depolarizing field. And we can see that actually if we introduce this term, we can obtain the negative slope, we can obtain that negative susceptibility, but this is bulk simulation. This is just motivation. It suggests that we could in principle look for that negative capacitance regime, but we have to consider depolarizing field. So that motivates us to look into films, because as we all know, films have a lot of depolarizing field. That is a good place to start. So we turn on to the to film simulations, and here we simulate 40 nanometer lead zirconate film. So we simulate different amount of surface charge compensation. We go from full charge compensation, ideal short circuit boundary conditions, and then we make charge compensation worse and worse and worse. And this is what we find. This data report the polarization response to the applied electric field. And as you can see, no matter what we do, we never find negative slope. But now if we report the polarization response to the internal field, which is once again the superposition of the applied and depolarizing field, this is when we see the emergence of that negative slope of that negative capacitance regime. So what happens if the surface charge compensation is very good, then the negative slope does not appear. But as we begin to compensate less and less, we can see emergence of the negative slope. So this computational data demonstrate that in order to reach that negative capacitance regime, we really have to introduce the depolarizing field, and we have to look into the response to the internal rather than applied electric field. So now, having established that, we went ahead and we took a look at what's actually happening at the atomistic level, and this is dynamical simulations. We're going to take a look at the time evolution of several things. So the red curve gives us the time evolution of our applied field, and the black curve is the polarization response to that applied field. So here the green data is the depolarizing field that we have in the sample, and finally the blue data gives us the superposition of the applied and depolarizing field. So the region of interest is right here. So as you can see, as we approach that switching regime, the polarization drops suddenly, and that causes equally sudden drop in the depolarizing field. And this is how we get that enhancement in the internal field. So that region where the polarization drop actually causes enhancement of the internal field. So that is our negative capacitance region. And as you can see, it is very short-lived. So we went ahead and we assessed that negative capacitance regime. We realized that if we are much below Curie temperature, the red data here, we have that very nice negative capacitance regime. As we approach Curie temperature, the blue set of data here, the loop shrinks. And of course, with that, we have less and less of negative capacitance regime region. And finally, as we are at the Curie point, we are above Curie point, there is no loop, there is no negative capacitance regime for us. We took a look at the dependence of the whole scenario on the frequency. We scanned frequency from 1 gigahertz to 10 gigahertz, and we can see the existence of the negative capacitance regime in all of these cases. We quantified the slope. So here we have ideal short circuit boundary conditions. The slope is positive. And then as we start compensating less and less, the slope becomes vertical. And finally, when we have poor charge compensation, we turn into that negative slope or negative capacitance regime. With that, I think I can conclude all three of my stories. And I hope that I was able to convince you that ferroics can exhibit very counterintuitive negative responses, and atomistic simulations provide us with a very unique, very useful tool to study that from atomistic point of view. So thank you very much for your attention, and I'll be happy to answer any questions you have.
All right, thank you for that very interesting talk, and also for leaving time for discussion, because I'm sure there will be a lot. I should start with my question, which is, you were talking about hybrid, hybrid organic and inorganic prospect, and that seems like an exciting new, place to explore for interesting behavior, and we've heard a lot about these systems. But how did you choose that particular system? It seems,
Right.
It's hard.
Right. It was actually motivated by one of my collaborators, who is an excellent chemist who can grow anything, and he's very good with growing this material. And we started to have a discussion about that, and then he said, "Why don't you take a look at these materials?" And I said, "Sure, of course, I know a lot about ferroelectrics." And this is when we realized that I don't know anything about ferroelectrics, because these are completely different materials. These are not displacive phase transitions. These are order-disorder phase transitions. And it turned out there's so much that we don't understand there that I completely agree with you. It seems like a very new, very interesting area to pursue, except that Alexey Gruberman, where is Alexey Gruberman? Is he in the audience? Yes. So he got some of our samples, and he played a little bit with them, and he said, "You know what, you are wrong. These are not good materials. We cannot measure them."
When you sigma 1, sigma 2, sigma 3, did you fix the volume or the volume is relaxed?
Volume is relaxed. So basically what happens, we apply stress along one direction, and everything, it's just like an experiment. Everything, yeah, we want to be as close to experiment as possible. Yes, everything else is relaxed. Mm-hmm.
Thank you. My name is Laura from Georgia Tech. I'm curious, in the type of materials that have negative piezoelectricity, are they also offsetting along the same directions?
We haven't looked at that. We should.
Yeah, I'd be curious to see if those two things are from.
Yeah, we should. But they do demonstrate the property that Ron Cohen predicted some time ago. Basically, for these materials, what happens, the polarization increases with pressure. So that much we tested.
Thank you for that. And I'd like to know your opinion. So, what do you think that the negative piezoelectric response could be used for? Can you do anything for that?
I think I'm going to borrow the answer from Andrew Rapp. I asked him exact same question when he was, presenting similar study. And he said that at least one possibility, if you want to keep your overall piezoelectric effect zero, then you can think about a material that has positive response and negative response, and then overall response is going to be zero.
Interesting to engineer spontaneous polarization, but no piezoelectric response.
Yeah.
All right.
And does anybody else have an idea about how to use a negative piezoelectric response? Yeah. Any other? Yeah. Definitely. Just put it out there. Negative piezoelectric response. What is it good for? You want to? Sure.
I think we work on the negative, but I don't work on negative suspension. Okay, so next to suspension that is very useful because if you behave some suspension, I think temperature, I see temperature effect that I can take. That's what the materials in the work.
Yeah, I mean, I'm not a transducer designer, but if somebody wanted to develop something that was very directional, for example, maybe some positive materials, some that had positive and some that had negative response to the field. Maybe very, very directionally negative. I developed something like that.
Other questions to move on? All right, let's thank Nina for talking. We're going to move to the last talk of this session from Louise Before. And she's going to talk about ferroelectric phase transition and the capacity of anti-ferroelectric circuiting cells. And she is a PhD at the